nucleus too.
Yeah. Did everyone hear that? Yesterday there was mitochondria, there was a ribosome, and there was a nucleus in the cell. We put that in yesterday just so you could see that this is a cell and it has the components of the cell just like any other body cell. But all right, the sodium-potassium pump is continually is moving sodium and potassium two ways. So we need a couple more potassiums. So you guys have already seen this. So 2 potassium get moved in. At the same time, 3 sodium get moved out of the cell. So you get you're constantly pumping out more positive ions, right, than you're bringing in. This leads to a net charge inside of the neuron that is negative compared to the outside of the neuron, which is now positive because you're pumping out 3 positive ions and you're only taking in 2 positive ions. Another thing that leads to the resting membrane potential are these negative proteins inside the cytoplasm of the neuron. So between the sodium-potassium pump, right, and the negative proteins inside the cytoplasm, you end up with a resting membrane potential of negative 70 millivolts. Okay? So calcium comes in, the vesicle actually, it's not quite endosymbiosis, the membranes merge together and the neurotransmitter is released right from the axon terminal. Alright, so it's not a full budding out of the vesicle, it's more like the vesicles merge and it releases the contents of the vesicle. It doesn't just release 2, and there's not only one neurotransmitter vesicle in the synapse, right? So there's going to be multiple in here, and it just releases a ton, not a ton, but it releases quite a bit of neurotransmitter into the synapse. Those neurotransmitters eventually make their way to the neurotransmitter receptor, right? Gets attached to the neurotransmitter receptor. It causes a conformational change in the neurotransmitter dependent channel. Neurotransmitter hits the neurotransmitter dependent protein or receptor, and it causes that conformational change. So the neurotransmitters bind, open up the pores, and sodium ions can now move into the cell. So we have a high concentration of sodium outside of the cell, lower concentration of sodium inside the cell. So when you open up those channels, that sodium is going to rush in. It's going to rush into the cell channels. Yes, exactly. This is called, it's becoming depolarized. So it goes from roughly negative 70 millivolts to negative 55 millivolts. Now, it doesn't always reach negative 55 millivolts. Negative 55 millivolts is your threshold potential. Yeah. So once your action potential has begun, there are enzymes in the cell body that cleave the neurotransmitter. That neurotransmitter, it gets cleaved into pieces, it gets released by the cell body, all right? It gets released by the dendrites and is reabsorbed by the axon terminal. So once these neurotransmitters are broken down, the conformational change is reversed and those sodium channels close back up. There's a protein, let's say it looks, I don't know, like that. That's not right, I'm just giving you an example. So say it looks like this. It fits into the receptor, right? An enzyme comes, it's a protease enzyme breaking down proteins, and it'll just cleave it up into its amino acids, into different sections. Right? Or let's say if it was a 4, let's just say we have 4, right, dots like this, it might come and cut it like this, split it up into 2, right, 2 or 3 pieces. You see, so instead of being one neurotransmitter, it cleaves it, it cuts the bonds, some of the bonds between the amino acids, splits up into 2 or 3 sections now of protein. Yeah, voltage-dependent channels, that's right, and there's voltage-dependent sodium channels. So what we mean by voltage dependent, when we're at negative 70 millivolts, the reason I have turned them on their sides is because they are shut off. They are not allowing sodium through at this point. Once this depolarization moves, right? So this portion is still negative 70, but this portion hits negative 55. These are open. And they allow sodium, again, to rush into the cell. Sodium's rushing into the cell. This will further depolarize the membrane potential. Will hit plus 30 millivolts. So that's all considered depolarization. Going from negative 70, you hit the threshold at negative 55, and then it goes all the way up to plus 30 millivolts. So eventually this, here's still negative 70, this will hit negative 55 millivolts. Again, opening up the channels, right? And these numbers are just going to keep moving. Bam, this one jumps up to 30. This one, this is still 70. This one starts going down. This is how that action potential moves down the axon. It's all about ion flow. So now, when we're talking here, once you get to positive 30 millivolts, that is the highest voltage that membrane will see. Once you get to negative 30, once you get to positive 30, thank you, your voltage dependent channels close for sodium. And what happens? So we get to plus 30, voltage dependent sodium channels close. All of the voltage dependent potassium channels, they open up. All right, so these potassium starts moving out, right? So it flows through the channels, out of the cell, through the channels, out of the cell, right? Same over here, through the channels. So those potassiums move out. This is called repolarization. So this is becoming repolarized. Some voltage-dependent potassium channels are always open. All right, always allows the flow. Not all of them. Once you hit negative 30, the sodium turn off.
Positive.
Pardon me? Sorry, once you hit positive 30, sorry, I'm mixing that up. Once you hit positive 30, the sodium channels close. The rest of the potassium channels all open. Right? The rest of them all open, and there's a huge rush of potassium out of the cell. So, because we've opened up the floodgates for potassium, and we still have, remember, the sodium-potassium pump is still working throughout this whole process, we actually get all the way down to negative 85 millivolts. No. And this is actually called, when the membrane potential is at negative 85, it's called hyperpolarized. So the membrane becomes hyperpolarized. The fact that this goes to negative 85 millivolts prevents the action potential from moving backwards down the axon. Because remember, I'm saying sodium flows in, and that sodium is going to change the resting membrane potential downstream on the axon. Well, essentially, would it not flow in and change the membrane potential upstream where it came from as well? Right? You would think that would be the case. But because these channels are shut off and these channels are all open, it actually goes back to negative 85 millivolts, and even once this starts to come back, the action potential is too far. This will eventually raise back to its original. I have it right here. So this will eventually get back to negative 70 millivolts, like this. So these move along, right? This moves along. This moves along. And then the negative 70 moves along. And the whole system just basically flows like this. You have resting, meets the threshold, gets up to plus 30, gets hyperpolarized to negative 85, and then comes back to your resting membrane potential of 70, waiting for the next action potential to continue down. On this side, right, these guys are all 70, 70 all the way down. This hits threshold again, opens up, and it is this, it's the voltage that it also activates this channel, yeah. So that's what, again, activates the calcium channel. Calcium comes in, and the membrane vesicle releases its neurotransmitters. What she's asking is, if this cell, let's just see if I get this right. If this cell is surrounded by multiple nerves, right? Say this nerve is not sending a signal, but these two are sending signals, absolutely, this can still fire. As long as it gets enough signal that you get up to the threshold potential, get up to -55, it doesn't